Okay, so this class we're kind of finishing off a few things in alkene chemistry. We're going to spend most of it on this one reaction, ozonolysis. Then we're going to touch on a couple of other things, and then we're going to shuffle over into doing some carbonyl chemistry after that. So assignment 2 online has a lot of this stuff, all this alkene stuff. There's a lot in the chapters of the textbook and the recommended problems as well. And again, I don't know how to say this as often as I could, just do more problems. So overall, ozonolysis is treating double bonds with ozone and then with a nucleophile. That's phosphorus. Like that P is actually one of those elements that we don't see very often. But the lone pair is on dimethyl sulfide. Keep my chat window open. Here we go. And what we're going to do is we are going to rip this open right at the double bond, and we're going to stick 2 carbonyls on it. So we're kind of slashing a knife right down to the middle of that double bond and sticking carbonyls on it. So it's kind of like an oxidizing knife, which is maybe a way to think about this. That's weird. So how do we go about how does this work? So this is, I think, along with the MCPBA, which is the epoxidation, and the boration, hydroboration, deboration mechanisms that we covered in the last few lectures. This is kind of the third of the trifecta of relatively complicated mechanisms that we see in this course. Then we're done to really hard stuff. Everything else is easier. I'm actually just going to leave the slide with that on it. I'm going to jump to the next slide. I said jump to the next slide. There we go. So part of the, I'll draw one up. Part of this is, what does ozone look like? That is ozone. You can draw a resonance structure for it, or you make the double bond on the other side. Either way, there's a lone pair on this guy, 2 lone pairs over here. That is not a happy molecule. There's way too many oxygen-oxygen bonds going. Like, 1 oxygen-oxygen bond isn't good. 3 of them sounds like a really bad day. So, I think it was last class where we saw the first time that the double bond act with the KMNO4, where the double bond acted like a electrophile instead of a nucleophile. We're going to see the same thing here. So in that KMNO4, we kind of had a negative and a positive side. We had that negative O minus and attack double bond. We're going to get the same thing here. It doesn't matter which side you attack first, because this doesn't really happen this way. I'm lying to you when I'm showing you the mechanism here. It's just I don't want to introduce a brand new concept. But theoretically, I'm attacking the wrong side, because if there is an intermediate, this does not exist. I wouldn't want the negative charge at the tertiary site. I'd want it at the secondary site. But once we have that, does not exist. The lone pair that on that carbon that came from the double bond is now pretty close to that oxygen. We're going to attack that oxygen. We saw this already, attacking oxygen with the hydroboration, deboration, and the MCPBA. And the KMNO4. But if we make a bond to that oxygen, we have to break a bond to the oxygen. Luckily, we have this big double bond to the other oxygen, and we can break that. And what's nice about that is it gets rid of that really ugly positive charge on oxygen, which we didn't want. So now we get this 5-membered ring with 3 oxygens in it. It's called an ozonide. So, ozonides, I like ozonides. I'm going to see if I can open something. I'll have to change my screen sharing. Where is it? I just remembered I have some video. Here we go. So I'm just going to stop sharing on this one. And I'm going to start sharing on this one. There we go. So this should please work. Dang it. Okay. I'm going to find this. I've got a video. It's buried then. It is in one of my folders, and I will find it eventually. In the meantime, you get a slight break before. Why isn't it opening my folder? There we go. Oh, and I'm sharing all my subfolders. Okay, that's awesome. I'm going to slide over here so you can look at a pizza menu from Naples. Not this year. You know what? Okay, I'm not going to find it. It's that maybe I'll show it next class so I can get my act together. Stop sharing from here. So what I wanted to show is what happens when you warm up an ozonide. And what happens is it blows up. Really quite spectacularly, actually. Like, really a lot of fun. Okay, pizzas. Well, you know what? It was what was available right here. I'm personally, I think on the Windsor Pizza Wars, I'm an Armando's kind of guy. But my real favorite is like slice of pie. I live in LaSalle. Slice of pie is the shit. And if you haven't had it, you need to have it. It's kind of like cheese wheels without the really awful without the awful labor practices. But it's like really, really good pizza. Anyways, ozonide, 5-member ring, 3 oxygens all bound together, blows up when you warm it up. Like really a lot. Terrifying thing to use. We use it all the time, and it's a lot of fun. So what you do then is this is where that second reagent comes in. I said, okay, you can then add number 2, US triphenylphosphine. Oh, sorry, I'm jumping the gun here. We're looking at this, and this is not a stable molecule. It spontaneously decomposes itself, if it can, into something even weirder. These arrows do not make the most sense in the world, and I'm going to grant that. So arrow number 1, we're going to use a lone pair on oxygen to kick down and make a new oxygen-carbon double bond. Why are we going to do that? Well, this is uphill. This is energetically unfavorable to do, but it's because we're going to end up in a more stable place in a moment. What that's going to allow us to do then is if we use arrow number 1, that's going to make 5 bonds to this poor carbon here, which can't happen. So it needs to break a carbon-carbon bond, and it breaks the carbon-carbon bond. And it generates a new carbon-oxygen double bond. So if you're counting at home, because where else would you be? You have 2 carbon-oxygen double bonds being generated in this step. Of course, that would mean this oxygen will make 5 bonds. You need 5 orbitals. It can't do that. It needs to break a bond. So it breaks its oxygen-oxygen single bond, which sounds okay because those bonds suck. So what do we get? We get that if you're keeping track of your electrons at home. That is awful. The thing on the left looks fine. The thing on the right looks like, a Halloween. Maybe I should go as that for Halloween next year. So that's not going to last very long. So what we're going to do is those two pieces are going to react together. So all I've done is I've rotated them around. And we know that a carbonyl has a resonance structure where you have the positive charge on carbon, negative charge on oxygen. We're going to spend a lot of time talking about that in our next lecture. So a negative charge attacking that carbon makes sense. It's going to push the electrons up onto oxygen. Again, I'm going to draw an intermediate that doesn't exist. If you're slowly going into like some sort of panicked shock mode, that's completely appropriate. So we have this guy. I do see the chat window still talking about pizza. And like I know this is like the most controversial thing you can talk about in this city is pizza. I figured that out within a few weeks of arriving in Windsor that as long as I had some opinion on pizza, I hated Matty Maroon for the bridge, and I looked down on Chatham, I could fit in Windsor. Okay, and we're going to close the ring like this. Again, so what we're doing is we're generating these oxygen positives, and then we're getting rid of these oxygen positives. So now we have another 5-membered ring that comes from this if you're trying to follow this along. This is called a secondary ozonide. I don't exactly know what the secondary refers to here. This is a primary ozonide. More stable. And it's more stable because you have more carbon-oxygen bonds and fewer oxygen-oxygen bonds. That seems pretty good. Carbon-oxygen single bonds are stable. Oxygen-oxygen bonds, it's just got lots of oxygen bonds. It's got 2 oxygens bound to other oxygens. Just that wants to detonate. So we have this guy down in the bottom right. It's more stable. Still not stable. There are examples where this has been isolated, though. So actually, we've made some of these and warmed them room to room temperature because they didn't react in this next step that I'm going to show you. And we're very confused by trying to figure out what the hell we'd made. And got really excited when we found out we made one of these and it didn't blow up. The thing is, we didn't know we'd made it until we'd already done the detection to figure out what it was. And at that point, if it had blown up, that would have been bad. But it didn't. So you get this. And then you need to do this next step because that is really, really dangerous. And we're also not at this product, which is 2 aldehydes, or 2 carbonyls on the prize. I'm going to start a new slide. So we have our secondary ozonide. Now, we're going to treat this with, I don't know, it doesn't matter. There's 2 reagents that do this. Triphenylphosphine is one. Dimethyl sulfide is the other, and they work in essentially the same way. you're looking at that molecule, and I know I want two aldehydes. So I've got all the atoms I need. It's just I've got an extra oxygen, so I need to get rid of an oxygen. And again, my products that we're going to just keep an eye on, what we're expecting to make. And then with the triphenylphosphine, we're going to have triphenylphosphine oxide. Yes, I did forget the methyl. You're absolutely right. Did I forget the methyl back here too? No, I didn't. Okay. So, after staring at this for a little bit, we're going to use the nucleophile. I called it a nucleophile, so it's going to be a nucleophile to attack something. I know I want to get rid of an oxygen. And if I attack that oxygen, I can put electrons onto that oxygen, break that bond. Let's see where that gets us. Doesn't matter. It could be either one of the two options at the bottom. It's completely mirror imaged. So the reason is one of those two options is because we're going to come back to this concept. It's a concept of a leaving group. There is the other oxygen can accept the negative charge well. If you attack the oxygen at the top, the one on its own, you would have a C minus being generated, and that's bad. So here we're generating an O minus, and that's okay. But I could have attacked the left oxygen instead of the right oxygen. It would have been exactly the same, and just the mirror image of what we're doing. So we have this. Probably put that in brackets again. Now, that lone pair comes down to remake an oxygen-carbon double bond. That's got to break a bond. I'm going to break that. So I got my product up there at the top. So hopefully one of you has already started drawing that. Again, phosphorus is weird. It can make more than 4 bonds because it's a second row element. So there. We've got our 3 products coming out of this. So overall, what the hell just happened? So what I've done is I've broken down all the steps. I'm gonna have another example now. I'm gonna use the other reagent instead, dimethyl sulfide. So just run through the mechanism one more time because this one really does deserve it, but I'm not gonna sort of stop at all the intermediates because they don't actually exist. So we go I think those 2 methyls are there. That methyl is here. I think everything's still there. I think I didn't lose a methyl this time. PPH3 is phosphorus with 3 phenyl groups. And I think we've already talked about how pH equals phenyl. Like a benzene ring. If you haven't seen that circle in the middle notation very much. 3 of those. Phosphorus with 3 of those. So that. Well, when I say they don't exist, what I actually mean is mechanistically, the mechanism, all these arrows get pushed at once. I've kind of stopped the arrow flow so we can sort of see where the charges go, so you can maybe make a bit more sense of it. But what I'm actually drawing this time now is I'm going to draw the proper mechanism. The arrows don't actually stop in the middle. They go through completely to the product. There's the things I stuck in brackets, those are never formed. They're things I've drawn so that we don't need to push all the arrows at once, so you can sort of follow them a little bit more easily. But that's not what actually exists. They kind of all the arrows get pushed at once. You either have the starting material or you have the intermediate. So here, but if you just draw it the way I'm drawing it now, it's really confusing. So note here now I've got a molecule that has a ring in it. So I broke the bond, but I just kind of opened a ring. So this is going to be one twisted bad boy. I'm now regretting drawing a three-membered ring. It's possible, but it's ugly. So we've generated, again, we have the five-membered ozonide ring. 1, 2, 3, 4, 5. And then we still have the carbons from the other guy. Okay. Now I take that, I add my dimethyl sulfide. And again, I'm going to stick an oxygen on this molecule, which is what happened to the triphenylphosphine. We stuck an oxygen on it. It attacks one of the oxygens. The other one snaps around to make an aldehyde, which breaks the aldehyde, the bond for that one, generating another aldehyde, which kicks the electrons back onto this oxygen. So if I count the arrow order, this is where, videos come into their own. So we have an order for the arrows. And what does that give us? Aldehyde, open, aldehyde, plus. And this is the solvent DMSO. If you don't know that solvent, it's an organic solvent. It gets used a lot in drug delivery. It's actually the major way we put drugs into people is using DMSO solutions. Because it's very polar for obvious reasons. So the nice thing about this approach is dimethyl sulfide really stinks. It's what they add to natural gas to give it that rotten egg smell, so you know when you have a gas leak. DMSO doesn't stink as bad, but it's a nice solvent, so it's easy to deal with. The triphenylphosphine oxide is a bit more of a pain. As far as you guys are concerned, I could not care less which one you want to use. I think I have questions with both of them now in the assignments. So note that overall what we did was we took this guy, we scissored open the double bond, and we stuck carbonyls on both sides. If you don't remember anything else from this, it's open book. You can have the mechanism in front of you. That's the really key thing that's happening. Yeah. Emmanuel, that is exactly what's going on probably in 114 minds in this class. There's 114 of you here. If you're not slightly confused about this, it's not going to get better. So I think what you need to do is you are going to need to, like, you can rewatch this, you can look at videos online with these kind of motions, you can look at the textbook, the arrow flow is going to be the same in all of them, and you need to practice doing it, and eventually it will make more sense. Like over here, what we're doing is we have a negative charge that wants to give electrons. Yeah, it really is the same thing. Yeah, D, that's a D. Yeah, it would actually, Mohammed. It's based this. There's only this one mechanism. It's a double bond gets cut open to give you two carbonyls. You probably should be lost. This is the most confusing mechanism in the entire class. I can say with quite a lot of confidence that because it would simply be regurgitation, I would not actually ask you this mechanism on the final exam. Because because it's copy paste. It really is. And if you can't copy paste this, then, you can't copy paste and then you're in trouble. But you need to understand what this did. That's really important. Okay. So we're going to going from something really complicated to something really, really simple. New topic: hydrogenation. You're adding hydrogen across double bonds. So far, ozone isn't actually that abundant in the atmosphere. There's a little bit of it very high up, but you really react to double bonds. And you generate ozone. The way we actually generate in the lab is we basically shoot lightning bolts into oxygen gas. And I have no better way of saying it than that, which is kind of metal. And that's exactly what happens in the atmosphere too. When you have lightning and you have oxygen, you generate ozone. And a lot of the ozone does react with things. That's why the ozone layer was at risk, is because we were pumping out these fluorocarbons, which were going up into the upper atmosphere, were reacting with the ozone. Not a lot of stuff goes up there, but fluorocarbons sure as hell do. And they start reacting with the ozone, depleting the ozone. Ozone doesn't come down to the surface very often, but occasionally, you get a lightning blast and you do get some ozone down at the surface level. And you can smell the ozone afterwards. And I always think of it as kind of like the smell you get after a really good thunderstorm. It's kind of sweet and spring-like and sickly, and really toxic. Now, the levels are so low in the atmosphere, and our bodies are really, really good at smelling it. So we're smelling parts per trillion, like really sensitive. But it's still really, really dangerous. Yeah, it is. Um, and it disperses pretty quickly because it finds things to react with. Almost smells kind of vegetal. Like there are some things in plants that smell a lot like ozone, which aren't ozone, which is really confusing to me. Because if they smell a lot like ozone, that tells me that they're reacting with the same nasal. You think about this for a second. Your nose smells things, right? I don't know how many different smells you can smell. I have absolutely no clue about these numbers. But the way that works is like there's a protein in your nose that interacts with that molecule in a specific way and stimulates a response, and your nose goes, hey, I've got this molecule stuck in my nose. Now, you must have a whole bunch of different proteins, each of them somewhat specific for all sorts of different molecules. And if they have a slightly different molecule attached to them, they register that something else happened. You smell a different smell. I get overwhelmed when I think about how the brain works. I get completely overwhelmed when I think about how nasal sensitivity works. Like how many proteins you must have in your body that all they do is they detect smells. It's exactly like that. It's all just fit in a protein pocket. Yeah, palladium. So this is palladium. This is like the metal palladium. Like really, really expensive. So you take hydrogen gas, you take palladium catalyst, and you get rid of the double bond. How does this work? Short answer is we have no effing clue. Longer answer is we make something up. So currently, the working theory is palladium metal is a whole lot of palladiums attached to each other because it's metal. So let's draw some palladiums. Yay, palladium. And I have no idea about the bonding of palladium. I'm an organic chemist. I'm not one of these freak inorganic people. So now we have hydrogen gas comes along, minding its own business. And it basically sticks itself to the surface of the palladium. Now, palladium is sharp. We call this absorption. So the hydrogen gas absorbs onto the surface of the palladium. I'm just going to draw a couple of palladiums this time because I'm really lazy. And I'm drawing this sort of arrow towards, I should probably draw it towards one of the palladiums. Even the inorganic chemists wouldn't like that arrow, and they're really sloppy with their arrows. So this hydrogen sigma bond is kind of interacting with the palladium metal. And then through the magic of electrons, something like this happens. Where the hydrogen gets split by the palladium. And so you suddenly have two hydrogen atoms attached to the palladium. But they're very reactive, and we're not really worrying about charges, and it's all very confusing. And then you have an unsuspecting double bond come along. Let's make it a ring. Everyone likes rings. I'll show you why I want a ring. Let's say it's that ring. Now, this mechanism is what I'm drawing because I'm an organic chemist and I get really nervous. I can't draw mechanisms. I have no idea if this is correct, and nobody does. No one knows how this works. It does, though. So what we end up with is the two hydrogen atoms adding to the same face of the molecule. So they're not trans to each other. They always add sin, and that makes sense because the molecule is approaching a surface, and a molecule can't have both its top and bottom side approaching the surface at the same time because that's just not how dimensions work. So the bottom side or the top side approaches the surface and grabs the two hydrogens. So this is black magic. I will not mechanism is approximate only. So I will never ask you for this mechanism because it's not a real mechanism. We have no clue how this actually works. It is pizza magic. For all I know, it is quantum tunneling of hydrogen atoms through a palladium metal because palladium is really soft and electrons kind of do weird things around big giant metals. And I really don't want to think about this more than I have to because it hurts my brain. But hydrogenation works. Yeah, a lot of metals do this actually. Platinum is another one. Normally the really expensive ones: ruthenium, rhodium, iridium, nickel. Nickel's not that expensive, so people get really excited about using nickel. The problem with the nickel is nickel metal doesn't do this very well. You need to attach all sorts of fancy things to it, and by that point, it's far more expensive than palladium. But mostly palladium and platinum. Now, I will often refer to this as palladium on carbon. So what I'll write is something like, you know, this is the notation you'll see a lot. It's not just me. I still really hate it. That P still does not look like a P. There we go. So what you do is you take some palladium metal and you put it on charcoal. Why charcoal? I have no clue. But you put it on something because palladium is really, really expensive and charcoal is really, really cheap. And so you don't need as much palladium. So there's some palladium on the surface and it does the chemistry. And so if we did this, we would expect, well, okay, let's draw, I'm going to draw two products. So we've added hydrogens to both of those, so double bond disappear because we added two H's. We know we had to add them from the same side. And so you could have added them from the top face of the double bond, in which case you get B, or you could have added them from the bottom face of the double bond, in which case you get A. So I guess the question I want to ask is A the major product, is B the major product, or do you get about a 50-50 mixture of the two? Getting a lot of B's. Got a capital B just to mix it up. Got some A's. The A's are coming in. The B's are coming in. Trans is more stable. Well, on trans being more stable, be careful about, we're going to come back to what that comes down to. Not as relevant here. And trans is really stable in 1-2 systems because they both can be equatorial, but in 1-3 systems you want them sitting, because if they're on the same side, they'll both be up equatorial or both be down equatorial. But if they're across from each other like that on a 1-3 system, like carbons 1 and 3 on a ring, then one will be equatorial, one has to be axial. Okay. I think there's quite a few votes. The answer is A. Why is it A? Because think about it. So what you have is this surface of palladium. And we're going to drop this molecule onto the surface. So here's our molecule. I'm going to kind of draw it in 3D. So here's an isopropyl group. It's probably going to sit equatorial. Shit. Okay, I'm you know what? We're not going to draw any twist boats. Fuck that. We're just going to make this, I'm sorry, something less crude. I'm just going to say with no bond in a ring, it doesn't sit as a chair. It can't. But, this is the upside. So if you have a surface, this guy here is big and bulky. I want my surface on the opposite side of the big bulky thing, because otherwise my big bulky thing is banging into my surface, and that's not good. So I want to add hydrogen from bottom. There's a methyl group on here. And so if we're going to add it from the bottom, that's going to push the methyl group up. Because as the hydrogens add, the methyl group goes from being flat to being up. You are absolutely right. Doesn't change the argument, but absolutely right. W? I think those are H's. Sorry, those are H's. It's just the H's on the metal surface. So that's hydrogenation in a nutshell. The last thing I want to talk about is my favorite reagent of all time. Um, I'm not calling them by reagents. I'm calling them by what they do. Just gonna call it carbonation. So we've added oxygen, we've added halogens, we've added hydrogen. What if we want to add a carbon to a double bond? So you have a double bond, and you want to turn it into a cyclopropane. So what we've just done is add CH2. And the reagent we use for this is this guy, CH2N2. Solvent is often ether, diethyl ether. So CH2N2 is called diazomethane because it's methane with two nitrogens on it. And dinitrogen methane was not used for no particular reason, and dinitromethane would mean two nitro groups. So trying to draw the Lewis dot structure of this isn't super trivial. I'll skip ahead and just do it. So I love this reagent because you can add methyl groups to things. But the reason I love it even more is it's horribly explosive and horribly toxic. Like the starting material that you use to make it is used to induce tumors in rats. Like if you want to give a rat a tumor, use the thing they use to make this stuff. And the reason it gives rats tumors is because it makes this stuff. And this stuff methylates DNA, which then gives you cancer pretty easily. It also explodes if you look at it wrong. Like if you actually shine certain wavelengths of light on it and you have a concentrated enough solution, it will explode because there's enough energy in the light to blow it up. If there's anything sharp that it ever comes into contact to, it blows up. If you heat it, it blows up. If you shake it, it blows up. If you tap it, it blows up. Like mostly it just blows up. Like it's a lot of fun. And the guy I did my first postdoc with, his dad was the one who designed the way to purify this stuff. And it's sort of specialty glassware that's all custom made and has no sharp edges and no seals. And I'm never ever going to do that in my entire life. I work with it. I make it and work with it in solution. It's a little bit more stable. It's a little less likely to blow everything up. But working with it neat. There's, about once every 2 or 3 years, some lab in North America blows up because somebody made a solution of this and forgot about it, and it dried out and blew up. It also used to be the first, when I was a postdoc, it used to be the first reaction I'd have any undergrad do was make this stuff with me. We do it together and sweat because it's relatively safe to make in solution, but it's does treat you to respect lab technique. Yeah, yeah. I think thinking about it actually might put enough energy into it to blow up. Now, why does it blow up? And it blows up because it desperately wants to be nitrogen gas. If you look at almost any modern explosive, they all work on the same principles. They desperately want to be nitrogen gas. One of my students stuck a Halloween thing, like something scary, on my door, and it's a molecule called azidoazide, but that's not the full name. Trinitroazidoazide. Anyways, it's a stupid molecule with way too many nitrogens. Nitrogen just wants to be nitrogen gas. Yeah, ether is underneath. Yeah, Victoria stuck that on my board. Thank you, Victoria. There we go, azidoazide. It is a ridiculous molecule with way too many freaking nitrogens. This is a dangerous enough molecule, and it's only got 2 of them. So what really this thing really wants to do more than anything else in its entire existence is become nitrogen gas. And it does it with 1 arrow. And what that leaves us with is a CH2 with a lone pair, because it had one there earlier. And it's neutral, because it was negative and now it just lost electrons and we got nitrogen gas. And that escapes and generates a gas cloud, and that's why it's explosive, because you build up this pressure. This is weird, though. Let's just look at this guy. So it's worth drawing the Vesper structure of this thing. What it's got a hydrogen in orbital. It's got another hydrogen, another sp2 orbital. It's got a lone pair. I should draw it going back into the page. And then it's got an empty p orbital. So it's both it's got a lone pair and it's got an empty orbital. It is both negatively charged because it has a lone pair and positively charged because it has an empty p orbital. That's just freaking weird. This is called a carbene. And they are odd. So we can draw them this way, or we can think of them as CH2 plus minus. They are both positive and negative. And so if you bring a double bond along and it sees diazomethane, the double bond is there. You have this CH2 plus minus. Just think about it as CH2 plus kind of thing, just like chloride, just like iodide, like Cl2, I2. You attack the positive thingy. Attack. Generate the positive carbocation. Now it's just minus. And now you got a minus near a plus. Snap that puppy shut. And that's just cyclopropane. So this is a way of adding a methyl group. Yeah. If you want, chemistry, fun chemistry things, there's a blog called, I think it's fun, but I'm a weird guy. There's a blog called In the Pipeline. It's written by, he must be really getting on now, because I remember starting to read this blog back in, around 2000 when he was starting. So he's 20 years older now, and he's a pharmaceutical professional. A lot of the stuff is about the pharmaceutical industry, things going on in there. It's sort of an insider's look at what's going on with new drug approvals and things about the chemistry. But he's a bench chemist, and so he has a section on there called Things I Won't Work With. And he's got a lot of examples of molecules that are absolutely insane and no one would ever work with. There's only a few groups in the world that would deal with these things. And most of the time people make them so that they can just show that they're going to blow up. And there's a blog post about azidoazide. They're very readable. And it's a good inside look on absolutely insane chemistry. He's also a really good writer, and he's a very funny writer. So he does talk about how people are going to blow things up. Second step, forgot the extra H. Yes, you're absolutely right. So I'm actually going to draw a line under this, because that is basically, we have now covered almost everything I want to talk about with alkene chemistry. The one thing we haven't talked about in a lot of detail, and we discussed it briefly, and we said, just reminding you, because it was a bit of a throwaway, is the Anti-Markovnikov Edition of Hbr or Hi or any halogen. And the way we did that, again, it's already in the notes, but I'll put in the notes again, is if you use Hbr and a radical initiator. The one I had in the notes was benzoyl peroxide. It's one that's in the assignment as well. I think there's another one I use, and that's called AIBN. These are cyanides. Again, you got nitrogen with two bonds between itself. It is well on its way to becoming nitrogen gas. Both of these are radical initiators. We are going to talk about radical chemistry later in the course. I don't really want to get into the mechanism of them right now, but they kind of fit conceptually with what we've done. So if you do not have that, then you would go a Markovnikov addition, and you would attack the H, you would generate the more stable carbocation, which would be at the tertiary center. The bromide would come in at the tertiary center. These are the opposite. So you get the anti-Markovnikov product. Yeah, this is all going to go up on Blackboard right after this lecture. So this is the end of alkene chemistry for now. We're going to come back to this mechanism. We're going to be mixing these things up with some other things. So starting next class, we're going to switch into talking about some carbonyl chemistry. And then we're going to talk about a little bit of reduction oxidation chemistry. So we're going to walk from an alcohol up to an acid, and then from an acid down to an alcohol, and figure out how to go from alcohols to aldehydes to acids, or alcohols to ketones. You can't go to an acid if you have a ketone. AIBN is this. It's just you can use that in place of benzoyl peroxide. I think I might have both in the assignment. Azidoisopropyl bisnitrile. I can't remember. Something like that. Yeah. Yes, so you need radicals to get the anti-Markovnikov. If you don't have that, if you just have Hbr, it's just Markovnikov. It's also why I made such a fuss about being in the dark when we were talking about the Hbr reactions, because you suppress all this kind of garbage. Azobis isobutyronitrile. Thank you, Victoria. So Brendan, this is anti-Markovnikov addition of H halogen. You need a radical. For Markovnikov, no radical. I won't ask, Bennett, why you know benzoyl peroxide so well. Yes, I can go back to the previous slide. Yeah. That's really literally how it's doing. You're generating free radicals on your face with benzoyl peroxide. That is literally how that works. And those kill things. And because acne are kind of open sores, basically the benzoyl peroxide can get in more easily, and it kills stuff around there, especially bacteria. To me, it's a really, really crude solution. It's kind of like carpet bombing things and hoping it doesn't do any damage. Everyone hates acne. That is the one nice thing about getting older, is that does go away. Okay, I'm going to stop recording after this conversation of acne.